righty. Howdy. My name is Adrian Correa. I'm with Pulaski Technical College. We're going to go over Quality Control Inspector, the module that covers house as a system. I'm going to talk to you about why we try to be so careful with homes and not break them. So let's get started here. Hopefully by the end of this session you're going to understand how to, to be able to discuss the potential for interaction among various building components and their mechanical systems that you're going to find in homes. Pardon me. And give some examples of how air sealing a home can negatively affect building durability and indoor air quality. So if we have mold growing, that's not a good thing. And then be able to recognize some typical leakage sites and explain how to deal with them. So a house is a system. We have various parts that come together to make up our home, and one part, the way that it works, affects many others. If we have, for instance, an exhaust fan, it can depressurize the house if it's strong enough. That's a bad thing. But when they all work together, then the house is comfortable, it's safe, it's going to be more efficient, more energy efficient, a lot more durable. And when they're not working together, it's going to cause problems. Now, some of these problems are going to be invisible. Some of them are going to be quite obvious. Some of them are going to show up today, like almost immediately, and others are going to take a long time to show up. So what are we talking about here? Well, one of the most common issues that we have is moisture or indoor air quality. And they're very closely related because moisture can lead, or high moisture can lead to mold. And mold can be an asthma trigger. It can also cause other problems, flu-like symptoms, etc. So let's start there. Let's talk about indoor air quality. So watch my blue and black dots, and down here in the bottom, I'm going to, oops, I clicked too fast, but we'll talk about them all anyway. Down here in the basement, we have concrete. This may be a crawl space. It may be a dirt floor, but the issue that we have anytime we build a home is if we don't put some type of vapor barrier, and in some cases a radon barrier in, then we can have gases, in this case water vapor, diffuse through the concrete and come up into the home. This affects our indoor air quality. Here in the kitchen, we're constantly producing smells from cooking. Sometimes people burn things. Even just in cooking, some portions of the food will burn. That can release CO if it doesn't burn completely. But we also produce a lot of moisture just from cooking. In the bathroom, same thing. As we bathe, we're producing a lot of indoor air pollutants. So these are areas that are high moisture areas. Now, what kind of problems does this cause? Well, if we have missing insulation or cold spots like here in the kitchen around this window, if we have missing insulation here, or even better yet over here in the living room, what can happen is you see this discoloration right here, that's representing condensation. So if we're heating the home in the winter, we may have cold air moving through this wall and maybe up the cathedral ceiling, or leaking from around this window, but keeping this wall cooler than it should be, keeping it below the dew point of the air inside, so we're getting condensation there. Same thing may be happening over here in the kitchen. Garages pose a special problem because we have a lot of pollutants in the garage, especially attached garages. Detached or unattached garages don't really cause a problem because we're not sharing the air from inside them. However, we have the potential with an attached garage to share that air. We can pull air in either through a fireplace, okay, or through natural combustion, natural draft, open combustion equipment. We can depressurize the house slightly and pull air in, but more likely it's going to be things like range exhaust fans, cook stove exhaust fans. Fireplaces can do it. In fact, they move a lot of air, something around 300 CFM, clothes dryers, and the like. And In our newer fireplaces, generally building codes are requiring that they have an air inlet to them so that they're bringing in their combustion air from outside, which is a little bit better. But something that we'll talk about a little bit later is that a fireplace is a net zero cooling, or a net cooling rather, appliance, not a net zero, a net cooling appliance, even though we don't want it to be. We want to get some heat, but the problem is it uses so much air for combustion. If it gets that air from inside, then from inside the home, then it's pulling it through the walls and pulling in cold air from outside. So only the room that the fireplace is in is going to be nice and cozy. All the other rooms are going to be cold. And in an attic, if we have an uninsulated attic, that can force our heating or cooling equipment to work much harder. We typically size our heating and cooling equipment to go to a certain R value in the attic, or something that's expected. If the home was never completed with insulation for some reason or another, or that insulation was removed because it became dirty from rodents and never replaced, then we can have, or it's just been moved off of an area, then we can have an under-insulated attic and a heating or cooling system that's having to work too hard. Here we have another problem in the attic. We have a can light, and these can lights act like little chimneys. The fire in them is the incandescent lamp that's in there, the bulb, if you will. It produces a lot of heat. That warm air rises, goes through the holes in the can. Warm air also can rise to the ceiling and come around the fixture where it's not airtight to the sheetrock. So we have a lot of air leaking through there. The byproduct of this is warm spots on a roof deck, especially when we have snow on the roof. Now here in Arkansas, we don't see a bunch of snow in central Arkansas, but we see enough that everybody here knows what an icicle looks like. However, ice dams are kind of rare for us, but a little bit further north, ice dams are quite common. An ice dam is when we have premature snow melt and the water moves down to the edge of the roof, which is called the eave, and the air temperature is still below freezing. That eave is going to be below freezing. So we have heat leaking out of the house, melting the snow. The melted snow or water moves out to the edge of the eave and refreezes, where it will create pretty little icicles, but it'll also create these mean little things called ice dams. And water will pool or puddle behind it. That's going to get under the shingles and ruin the roof deck and the sheetrock inside. Another issue that we have is we put in an exhaust fan in the bathroom to take care of moisture from the bathroom. Bathrooms are typically pretty warm. We keep them at a pretty good temperature when we bathe to be more comfortable. But we also put a lot of moisture in that air, and then we pump it into the attic if we're not vented to the outside. This is not vented to daylight. It's pointing towards a soffit vent. Somebody tried to do the right thing here, but it's not working. And that's evidenced by this picture on the right, where we've got a lot of water damage. So the water's condensing. That moisture in the air is condensing and causing water staining, and it's causing structural damage to the roof deck and to the trusses. So why do we care about air leaks at all? Why don't we just let them happen and live with them? Well, let's talk about, first of all, what's going on with an air leak. When we heat up the air in our house to make it more comfortable, it rises. It rises to the top of the house, and if there are holes there, it goes out. However, just like you cannot put your finger on a straw and lift it out of your drink and have liquid run out of it until you move your finger off the tip of it, air cannot leave the house until you remove your finger off the tip. In other words, it needs two holes. It needs a hole up high and a hole down low. And that's one of our rules of building science. For 1 cubic foot of air to leave the house, we have to have 1 cubic foot of air come back into the house. And we call this air exchange. It's not really ventilation. Ventilation we're going to define as a controlled leak. These are uncontrolled leaks. They're going to happen faster as the temperature from the inside to the outside gets bigger. And air is going to come in anywhere it can. We really can't control where it comes in. So when it gets into the attic, this is one of the issues that we have. If you look at the little white dots, those are nails with frost on them. More moist air from inside the house has come up and frozen in other words condensed and then frozen, onto the nails. The nails are below the dew point, the temperature at which water is condensing, will condense out of the air, and it's also below freezing, so it's creating frost. You can see that this is an ongoing issue. We have a lot of discoloration on the bottom of this roof deck, which might be caused either by frost. We have saturation here, so we're getting condensation on the wood. Moisture doesn't really like to condense on wood until the wood becomes saturated. That can happen in the winter when you have roof decking over a hole that's leaking warm, moist air all the time. So in the areas where it's not saturated yet, then it's not condensing very heavily. Another issue we have is around plumbing pipes. Plumbing pipes go up through generally our walls, and they pop up into the attic, and where they do, the holes are usually much too large. They're bigger than they need to be, and they allow a lot of air to move through them from the stack effect. Again, that's just warm air rising. So as that warm air goes up, it takes moisture, and we're just filling our attics with moisture in the winter. And that's one of the reasons we ventilate our attics, is to try and get rid of that moisture. Now here, what we would do is come in and we would seal that hole, air seal it. But look for dirty insulation. That's usually a telltale sign of air moving through insulation. The insulation is filtering out the dirt. The other thing that we want to look for while we're in the attic is a chimney chase. And chimneys run from the top to the bottom of the house usually. And in a multi-story building or a home with a basement in it, that's probably the tallest stack that you have in the house, which means that you've got a long way for that air to move up. And the longer the path that it has to rise, the stronger the stack effect becomes. So the faster air will move out and the faster air will move in at the bottom. So we need to block this off. So how do we do it safely? First of all, we're dealing with a block chimney, what we call a masonry chimney. And we want to remove the insulation, move it back temporarily, so that we can then come in, look at the top right slide here, or fixture on the slide. We want to make sure that we have clearance to combustibles. We need minimum of 2 inches around a masonry chimney. Okay, I would recommend going to 3, but a minimum of 2. Okay. Here, these gentlemen in the bottom left slide, they're installing blocking or nailers to put down sheet metal, so that we've got something to attach the sheet metal to. Excuse me. And we also have something to seal the sheet metal to. If we just span that area and we don't seal it, it's not air sealing. Air is just going to come right under it. So we've got to have something to form an air barrier, to complete the air barrier for it. The other issue that we have, or the other thing that he's doing here, is toenailing these two pieces of wood together. Let's look at the next slide here. On this next one, the sheet metal's been installed, and we have a high temperature caulk or high temperature sealant around it. Typically, this is going to be a high temperature silicone. Now, you need to look and see what is allowed. The only thing that I recommend is a high temperature silicone. I haven't found any other sealants that meet the ASTM specification that CFR 440 Appendix A, which is what the DOE's material list for air sealing is in. And there's an ASTM number for sealants, and this is the only stuff that meets that specification. Over here on the right, we have put in a metal air barrier, a metal dam. I'm sorry, not an air barrier, an insulation barrier. We put in a metal dam, is another name for it, to keep the insulation back from it. The reason is the insulation, even though it's treated with fireproofing, is still considered combustible. Okay, this is another chimney. This one's made out of brick. But we're doing the same thing. We're just moving the air barrier portion of it down into the home. So up top we have this perforated metal. It's not perforated, what do I want to say? It has these pre-formed folds in it. It's called Insul Shield. It's kind of nice because it does have those pre-formed folds. It's easy to wart back and forth, kind of like a paper clip, and you don't have to cut it. It's got these tabs on the bottom, nice to put screws in. So here they're creating the air barrier, or they're making their air seal on the inside of the house. Typically we do this in the attic, but I guess because of dirt or other issues up there around the chimney, they decided to do it inside. This is being done in Maine, and their weatherization program allows them to air seal on the inside with their client's approval. So this is a technique if you cannot access the area in the attic, other than to put a dam around it, to try and effectively air seal, or you've got degraded components around it that are not forming structure, that don't need to be repaired. This is a way that you can make an air barrier repair inside the house. Let's go to the basement. Down in the basement, water is typically the problem. If the foundation wasn't waterproofed, doesn't have a proper footing drain around it, then you're probably going to have water in it. This one seems to have gotten quite a bit. In fact, we have a stain on here that's creating our high water mark. We also have a lot of water in that sump. The sump is not covered. That can lend itself or allow evaporation. That evaporation is going to put moisture into the block, and if that moisture condenses and freezes, it's going to create what the problem that we're having over here, which is spalling. Spalling is a term for concrete, stone, or brick, or block being blown out, chunks of it being broken from frozen water. And if you don't have the proper type of brick or block, like on a walkway, you'll see the walkway damaged from it. Here on the top right picture, we're seeing mold-like substances on the floor joists and on the walls. And then here, now they're saying this is spalling. I don't necessarily agree with it. It doesn't look like spalling to me, but the picture is not very good. It may be broken pieces out of the block. What it appears to be to me is efflorescence. Efflorescence is when salt deposits are left by evaporating water. Okay, so let's move to the next one here. So look up at the subfloor. Here we have a subfloor that's made out of, it looks like 1x6s, probably tongue and groove, but we have a large hole that was put in the bottom of this bottom plate, okay, to allow a plumbing pipe and a wire to go through. And this needs to be blocked off. We need to be careful not to use a foam product here if that foam product is going to contact the interior space at all, or the conditioned space. We can't have exposed foam in a conditioned space. It creates a fire hazard, violates fire codes. Building codes don't allow it. It needs an ignition barrier over it. So here we'd want to cover this and use a sealant over it. We don't need to use a spray foam over it. Plumbers, wow, plumbers get a bad rap. You know, we do the best job we know how to do. What winds up happening, though, is we create building science issues or broken buildings. We've got a big hole for, varmints to pass through, so this hole doesn't meet code. It should have been rodent-proofed. But the other issue that we have here is that we've got a giant hole for air to pass through. We need to cover that, so we'd cut metal or wood or something to cover that. This is the same thing, only older. We really haven't changed our bad habits. We're still making giant holes around bathtubs. We're just using different materials to put in those holes, meaning galvanized pipes instead of plastic. Still down in the basement, we're looking at a plenum and a supply duct, and where these two join, we've got a large hole. And the most likely reason for this hole being left here is this piece of wood on the left is a floor joist. So we're looking at the area between the subfloor and this ductwork. There's not a lot of room to work in there. So trying to get their typical tools in there, and you can see how they've joined these two. They've just used a piece of sheet metal screwed between the two. Well, that's not air sealed. And we're putting pressurized air into this plenum and this duct, and it's going to blow out through that hole at a pretty good rate. We're putting a lot of conditioned air into an area that we didn't want it. We didn't put registers in there, so we don't want that stuff down in there. Another issue that we have is our combustion appliances down in that area. We have a vent here with a barometric damper, and that barometric damper has been dumping exhaust gases into this return register. This is a return register on the furnace, and you can see evidence of soot right here under my cursor. That means that we're probably producing carbon monoxide. That carbon did not link up with enough oxygen during the burn, so it only has one oxygen with it. That's carbon monoxide. If it had two, it'd be carbon dioxide. Carbon dioxide and water are the two components you get out of a good complete burn. Carbon's a sign that we don't have a good burn. It's incomplete, so we're producing carbon monoxide. The issue here is we're pulling that into this return register and then distributing it throughout the house. It's going through the furnace and through all of our supply ducts and out the registers, and it's probably poisoning this family. The other issue that we have over here to the right, and I guess the plumber or somebody tried to address this issue, they've put control systems on here to shut down. These are called spill switches, if you will. They're a thermocouple designed to heat up and shut down the gas circuit on this water heater when the unit spills or backdrafts. But the real culprit, again, is this open return register and this barometric damper located so close to it. This is a really poor design, just begging for somebody to get hurt. Let's talk about garages for a minute. In our garages, we tend to store a lot of stuff that we probably shouldn't. We store a lot of things that are poisonous or that can potentially be poisonous, but they compromise our indoor air quality. So sometimes you'll walk out in the garage and you'll smell cleaning products or solvents or gasoline that's being stored in there. We also park our vehicles in there. They produce carbon monoxide. Especially when they're cold, they produce high amounts. And with an attached garage, you have the potential to pull those poisons into the house and compromise your indoor air quality. Not a good thing. One of the ways that we try and defend against poor indoor air quality is to put in spot ventilation. Now here on the left, this spot ventilation is a range hood. We've put it over this stove, and hopefully it's going to pull moisture and grease and other things that are produced when we cook and take them out of the house. That's great if it's vented all the way to the outside. In the bathroom, what we're looking at here is water damage that's occurring over the shower from condensation. We probably have a lack of insulation over the top of this drop ceiling, and that portion of it staying pretty cool, and we're growing mold in there, or a mold-like substance. If we had an effective vent fan, then we would keep that moisture from building up, especially if it were being used while people are bathing. That's another issue. Is generally I recommend a bath fan with a humidistat, and a humidistat is kind of like a thermostat, except it measures humidity and turns something on or off. So a humidistat on the vent fan would turn on when the humidity goes up and turn off when it drops back down, much like the thermostat for our furnace. Another area of concern is a drop soffit. Now a drop soffit, or a soffit if you will, is sometimes called a valance, but it's a section of the ceiling that has either been dropped down to meet the cabinets, or you can consider the wall being bumped out to meet the edge of the cabinets, but it's to keep grease and dirt from building up over the cabinets and provide a more finished look to the cabinet installation. But you can see with this drop ceiling here, these rafter or joists that are creating the ceiling are sitting on a ledger attached to the studs on this wall. Well, the top of the studs are open, so air can easily pass through. Let's take a look at this next slide. Here we've just changed our angle. We're now looking at it from the attic side. So if you see soffit mounted cabinets, the thing to consider is that you're probably going to have air moving up through there. The other issue that we have is that our thermal barrier and our air barrier, let me go back one slide here. Our air barrier is this sheetrock and this sheetrock. So the sheetrock under the ceiling joists and the sheetrock on the front of this framing, that's our air barrier. However, when insulation is rolled out, it's just going to be on top of these, either in between or on top of these joists. It's not going to dip down into the valance area or into the soffit. So our thermal barrier, which is that insulation, is not going to follow the air barrier. We need it to, because when they're not touching, you can have a convective loop that starts in there. That means more energy transfer, and it also makes our insulation work become less effective. Our insulation is not doing as good a job. I talked about fireplaces being net cool devices. And this is true on all but the smallest of homes, because what you have is a fireplace that throws a lot of radiant energy. That's primarily the way they heat, is through radiant energy into the room that they're in. But remember that radiation is a line of sight heat transfer. So only the things that can see that's in quotes, that are in direct line of the fireplace are being heated up. Everything else is being cooled because this fireplace is probably using somewhere close to 300 cubic feet a minute of air for combustion. And of course that's going up the chimney. So where is it coming from? Well, it's coming from inside the house. If there's not a dedicated air supply to this fireplace, then it's going to pull air through the walls of this house, through the cracks, through the crevices, and that's air that we can't control. We can't filter it and we can't condition it. It's coming into the house, being conditioned, changing the temperature in the other rooms, actually dropping it, because you're not going to run a fireplace in the middle of summer, especially here in Arkansas, but you might run one in the middle of winter. And you're going to be pulling cool air, cold air in from the outside, so we're going to have to raise that with the furnace, and then it goes right up the chimney. So what did we solve? I guess our need for romance and a wood fire, but we didn't do much for our energy bill. So just bear that in mind next time you light an open fireplace like that. Don't light it because you're trying to be energy efficient. Light it for a better reason than that. Unvented space heaters. Oh boy. Unvented space heaters are a real problem because while they're vent-free, they are not poison-free. Now this is for combustion appliances, is what I'm talking about. An electric one, yeah, that's going to be poison-free for the most part. It has its own safety issues. But aside from the safety issue of having an open combustion source inside the house, the biggest problem that you run into is moisture. Moisture is a byproduct. Remember I told you you get two things from combustion, carbon dioxide and water, along with heat. Well, we're getting the heat in there, but we're also getting the carbon dioxide and the water. If you read, like for a modern gas vent-free space heater, one of the first things it tells you in the owner's manual is open up a window and verify that you have enough combustion air available, 50 cubic feet per 1,000 BTU of input, and then it'll probably tell you open up a window anyway. So I've never understood buying a heater that the very first line of the instructions are open up a window, because that's where the cold is outside. Now it's telling me open up a window and let the cold in. Well, they're not asking for the cold, they're asking for combustion air to dilute the byproducts of the space heater. The other thing is, if they get dirty at all, they stop burning efficiently, and your efficiency goes down. That means that your potential for carbon monoxide goes up. We'll see all kinds of things. And as far as putting water in the air, kerosene is about the worst. It has the most water in it for liquid or gas fueled space heaters. Let's talk about the outside of the house for a minute. When we have cathedral ceilings, they're usually problematic. They're hard to keep dry. They're either over-ventilated or under-ventilated, or they have a lot of air leaks into them. And your air leaks are going to come from things like recessed cans and skylights, etc. If they're over-ventilated, they can pull, especially here in Arkansas where we're cooling a good bit of the year and really refrigerating our air. They can pull that cool air into that warm attic area, because let's face it, that's what it is. It's a very small attic. Pull that warm, moist air into that attic area and it can condense. The warm, moist air that's in there will touch something that's cold. That cool air is cooling down, cause condensation, provide a very good habitat for mold. The other issue that we have on the outside that we need to watch for is shrubbery and trees right up against the building or too close to the building. This is an older home that we're seeing here on the right-hand side, and we've got a lot of greenery right up against it. This greenery is preventing air from circulating and drying this house. The way this house is designed, it's designed to dry to the outside. Any moisture that gets in to the walls wants to move back through the clapboards and out. But if we don't have good air circulation, which in this case is being cut off by all this greenery, we're not going to have good drying. Okay. Exhaust appliances. Now we're getting into our mechanicals. Dryers are exhaust appliances. Keep that in mind. Always keep that in mind. If they take air from inside, even electric dryers, take air from inside and pump it to the outside. They fill it full of moisture and then pump it out. We want it to go outside. That's some of the price that we pay. However, if we have natural draft appliances, combustion appliances in the house, then they're going to compete with those for air. And we have to make sure that when we tighten the house, we don't tighten it so much that the dryer finds it a lot easier to pull air down through the flue for the water heater than it does through the leaks in the house. Then we also just have over here on the right hand side regular old vent fans. They will also compete with our combustion appliances. Then we get into client lifestyle. Client lifestyle is interesting because you never know what you're going to find. You think you've seen it all, and you go into somebody's home, and boy, you're seeing something new, or a new take on something you thought you'd never see again. Pets can compromise indoor air quality. When we're making calculations for ventilation, we need to consider the size of the pet. ASHRAE doesn't speak directly to this, but my recommendation is that if you've got 30 or more pounds of dog, you need to consider them as another occupant. Imagine if the homeowner had a 30-pound child. You would definitely count that child as an occupant. Well, dogs live and breathe. Cats live and breathe. So for about every 30 to 60 pounds of animal that you have, you need to consider that another person. If they're under 30 pounds, well, you can consider that somebody in the house is just a little overweight. Yeah, we won't talk about overweight anymore for a while. How about all the house plants? When we water plants, we're putting water onto the plant. However, as part of the life cycle of the plant, it uses that to transport nutrients from the soil up into itself, and then it gets rid of its excess water through evaporation. So really the water wants to go one way. I guess it gets rid of waste by pumping water back down. I'm not sure. I'm not a biologist, but I know it goes one way for sure. But a lot of that water evaporates. It either evaporates through the leaves or through the soil. And if you have unglazed clay pots, it can evaporate through the clay pot itself. So all of the water basically that we're putting on the house plants winds up in the air. That's going to raise the relative humidity in the house. That needs to be taken into account. How about this bottom right-hand picture? This person is drying firewood in their basement. This is not an uncommon sight when you get into areas that have a lot of wood heat. A lot of people that are challenged financially may own property or be able to get wood at a very reasonable to free rate. In other words, they just put their own labor into it and that's it. So for them, it's a very economical way to heat. However, it's not a good thing simply because, or to dry it inside the house, because all of that wood, which can be, don't quote me on this, but I think about 4 quarts a day. Maybe it's 10 quarts. I'd have to look. But anyway, it's quite a bit of moisture being put into the air, much more than you want, much more than a family of 4 is going to normally put in there. So drying wood inside the house, not a good thing. Let's take a look at an occupant behavior here that is causing a problem that you might be asked to solve. So we have a set of windows here, and we have divided lights on the side. That's what these little bars going up and down here, we call those divided lights. In older windows, excuse me just one second, let me turn my mic off and cough. Goodness, that wasn't nice. Sorry about that. So in older windows, these would have been individual pieces of glass in each one of these sections. In newer ones, you may have a plastic overlay or something that gives you the illusion of a divided light. But we have a lot of condensation in this middle window here. We don't have any condensation on the sides. So what's causing this? Well, here's a clue for you. Right down here in this left-hand corner where my cursor is, we have a blue and yellow and white sticker still on that window. So first of all, why do we have the condensation? Well, we've kind of discussed that. We've got a lot of houseplants here. And so the moisture is probably coming from the houseplants. If it is winter, if it's cooler outside, then we're going to get condensation on the glass if it's below the dew point of the indoor air temperature, which evidently the middle pane of glass, this one right here, is. But why are these not? Well, the answer is that these two have been replaced. These are double pane units, so they have a higher R value, in other words, more insulating power than this middle unit does, which is still a single pane of glass. So what should be done? This is another picture. We've stepped back. Now you see a ceiling fan up here. Get a better view of what's going on. We can add a storm window. We can cover that center window and raise the R value on it. We can replace that center window with a double pane unit with a higher R value. We can advise the homeowner, hey, you need to run that ceiling fan all the time. Put it on low, let it stir the air so that we're not condensing air on it. We're keeping that glass a lot warmer by pushing more warm air next to it. Or get rid of the plants. There is no one right answer. You're going to have to talk to the homeowner. What are they open to? If they are open to get rid of the plants, that's probably the cheapest, best answer. Are they going to really run that ceiling fan? Some will, some won't. You're not going to get them to run that fan all the time. They'll tell you. So you need to be honest with yourself and ask your client to be honest. Are they really going to run that ceiling fan, or is this going to continue to be a problem? And is the structure going to be damaged because of all the moisture that's condensing on that window running down? And what about the indoor air quality? That moisture is going to mix with the dirt. The dirt probably has mold spores in it. They're going to do their thing and make more mold. So we're going to have an indoor air quality problem. Does the homeowner have breathing problems at all? Is there a child that suffers from asthma? Can they afford to replace the whole unit? Can they afford to add a storm window? As I said, there's no right answer. Your program, your funding, and your client are going to all help you decide what you need to do there. So it all depends on what you run into with your client and your money. So here's something to think about. Our houses today are a lot tighter than they used to be. They have a lot more exhaust appliances in them. The natural draft appliances that we're putting in them are weaker. In other words, they have a lower input BTU rating. Input BTU means how much gas or oil or coal do they use and produce their heat. The higher the input BTU, generally we consider the bigger the unit. So we may have a home that was designed for 50,000 BTUs 60 years ago, and we find, or that's the heating load calculation on it, but we find that we've got a 100,000 BTU furnace in it because we may have only been burning at 50% efficiency. But today, probably the crappiest furnace that you can buy is an 80,000 or an 80% efficient, which means that we, in the same house, we can probably get by to keep up with that 50,000 BTU heating load with a 65 to 75,000 BTU furnace. The other thing to consider is that our houses have less drying potential. The way they're built, they dry to the inside, not to the outside. So let's take a look at that. In older homes, we would have a rubble and mortar foundation, or a block or a stone foundation. We would have air leakage right at the sill plate. We still have that problem right at the sill plate. But our subflooring was probably going to be tongue and groove 1x material, or non-tongue and groove 1x material. So when the 1x shrinks in the winter, what happens? We get gapping between the boards. The stuff is laid in there so it doesn't cup in the summer and bow up from the moisture. So we've got to have a little bit of gap there. Well, that's a good place for air to leak. Same thing's happening on the sheathing on the sidewall. We're either using a skip sheathing for economy of material. That means that we put one on, skip one, put another one on, skip one, put another one on. We only need it for nailer, and then we will nail the siding on it. But today we're using plywood, and plywood products are a laminated product. They're veneers of wood that are glued together, or they're chips of wood or strands of wood that are glued together under pressure. And when they get smashed together like that, there's fewer air paths in them. When we put the glue in there, we're closing off even more air paths. So what happens is if water gets in the wall, air is not going to move to the outside of the house very easily. In fact, it's going to move to the inside much more easily, and that's where the moisture is going to be carried. A wet wall is going to try and dry to the interior. Another thing that we had is that today we may have very powerful downdraft appliances. The fans on these downdrafts are very strong because they have to turn the draft around. Remember, the stack effect is warm air or warm fluid rising, and a fluid you can think of as a gas or a liquid. In this case, we're talking about air. So we warm that stuff up, and it wants to rise up. Well, this fan has to be strong enough to get it to make a U-turn and go down through the ductwork to the outside of the house. On this right-hand picture here, we have a range hood that probably all of us grew up at home with one of those. Whether it went to the outside or not was anybody's guess. Without looking at the ductwork and following it, you just don't know. And then some of us may have grown up in a home with a range fan that looked like this one on the bottom left. Just a bezel with a fan motor kind of attached to it and a flapper on the outside. And when you opened up the flapper, which was just another piece of aluminum, the fan would turn on, and that's what took the smoke and cooking mess outside, hopefully. So we talked about having weaker draft appliances. Let's take a look at why. Here we have a wood-burning open fireplace. It's open combustion and natural draft. We started putting glass in front of it to prevent a lot of air going in and also to contain sparks and ash and that sort of thing. But down at the bottom we have a lot of venting there to allow combustion air to get in there. So now we're getting enough combustion air in there to support the fire, and we're not getting a lot of dilution air, which is additional air going into the fireplace. So we've slowed down how much air the fireplace is using. So that's going to slow our air loss a little bit. Look at what is available today. We have these highly insulated wood, or not insulated, but we have these highly efficient wood stoves which are bringing in combustion air from outside and throwing a lot more radiant energy. Look, we've got excuse me, 5 sides now to radiate energy off of, and here they've put a high thermal mass brick behind it, also for combustion safety, clearance to combustibles. But that brick is going to re-radiate heat into the room. So we're throwing a lot more heat into the room than we used to. But the other thing is we're bringing combustion air from the outside. We're not taking it from inside, so we can put that in a much tighter home. Pardon me just a second here. I need to rearrange. All right, so let's take a look at central heaters. Here we have an old coal-fired boiler that was converted to oil and now has an oil burner on it. And that thing is probably about 50% efficiency. Then we go to a high mass boiler, which has a lot of cast iron in it. Takes a long time to get going, takes a long time to cool down. And when it's off cycle, meaning it's not burning, if you don't have a damper on the flue, then a lot of that heat is going to go right up the flue because of the high mass. There's a lot of residual heat left in the unit. And those were only about 80% efficient. Then we go to a low mass boiler. These things come up very fast. They produce a lot of heat. And most of that heat is transferred right into the water. Only about 10% goes up the flue. And since they're so low mass, even during off cycle, they don't lose a significant amount of their heat because there's not a significant amount to lose. The recirculating pump tends to stay on and pull that extra heat off. So we're only losing about 10% up the flue. So we have smaller, lower BTUs. This big 50%er, if we're trying to put 100,000 BTU into the house, then we might need a 200,000 BTU boiler. However, down over here, we can put 115,000 BTU boiler on, and now we've cut the size of the boiler almost in half simply by going to a more efficient boiler. Okay. Again, today's homes have less drying potential. The old house got wet in the summer from the humidity, and in the winter it would dry. We generally have lower humidity. They were balloon framed to allow air to move up through the walls. Had lots and lots of stack effect. Also had lots and lots of moisture-loving stuff. We had clapboard siding on them. We had skip sheathing or tongue and groove sheathing. practically no insulation, so we needed a lot of high mass boilers to put a lot of heat into these things. And the construction materials and styles, that's what was available, but the style was designed to be leaky for safety's sake. It was designed to be leaky. Then we got into the 50s, 60s, and 70s. We started building ranch homes, these lower one-story. So the stack effect is not nearly as strong, and that means that the drying effect is not going to be nearly as strong. We're building with plywood and drywall. Now the drywall is no more water or no less water loving than the plaster, but the plywood is. The plywood tends to be a little less water loving than just sawn lumber, which is, you know, like a stud or something like that, or the 1x6 that was used for the sheathing. The construction style and materials are inherently tighter than in the older homes, so we have a lot less air circulating through the walls. Newer homes tend to dry to the inside. Older homes tended to dry to the outside. And then we've got lifestyle changes. Here we see some folks playing video games. That tends to be the norm. We spend a lot more time inside with the doors closed and the air conditioning or the furnace running. We do get outside and play a little bit, but the point is we're spending more and more of our time at home. We're also moving closer to the sources of where energy is produced along the coast. In Houston, you can't step outside on some days without smelling an oil refinery or a chemical plant when the wind is just right. Other days you don't smell them at all. But sometimes the outdoor air quality is pretty bad. How about gardening? You know, we may have a great love of the outdoors and plants, but if we bring it inside, we're going to cause problems inside the home. This is a little bit different than we saw through the 70s, where not as many people were into gardening. In the 60s and the 50s and earlier than that, a lot of people grew gardens because they had no choice. They needed the food. That was the only way they could afford food. And then how about the way we tend to nest on Saturdays and Sundays when the big games are on? We get everybody over there. That drives our indoor air quality down because we have more people breathing, you know, beer breath, and those things that happen after you drink too much beer and eat too many potato chips. So let's sum all this up. We build differently than we did 40 years ago, and we have different lifestyles than we did 40 years ago. Economic pressure is driving us to build tighter and tighter homes, and we have smaller margins of safety as far as indoor air quality and air exchange rates go, as well as providing enough air for combustion. The tighter the house is, the more influence individual components have on the others. So a fan tends to have a lot more influence on an open combustion water heater that's natural draft when it's in a tight house than it would if it were, you know, same size house but much looser. In other words, a higher blower door number. And all indoor pollutants inside the pressure boundary are going to be dispersed over the entire area. So think about this. Would you rather be subjected to somebody breaking wind in a closet or in a gymnasium? You're still going to have a dispersion over the entire area, but you're going to smell a lot less of it in the gym than you would in the closet. So we want to try and exchange the air. So we can't live in a gymnasium. That wouldn't be practical. But we can exchange the air so that we do get good dispersion or dilution of the pollutants and get them out of the house. If we mess with a building or its mechanicals, then we need to expect that something's going to change. We need to test in, baseline what the house is doing, how it's operating today, and then as we change things, we need to test out. We need to make sure that we're testing every time we make a change to that house before we go home to be sure we're not leaving a dangerous situation for the client. We'll see you on the next module.